intro and then we can start.
Okay.
There we go. Hey guys. I'm Mohammed. I'm the propulsion lead for SEDS IIT. I have with me Maciek today. He is Maciek.
Hey, what's up, guys?
There we go.
Yeah, I'm the technical leader. If you ever have any technical questions about your rockets, feel free to ask me anytime, anything.
Alrighty. Before we start today about this presentation, I'm just going to give a little update on what's going on with propulsion and SEDS IIT in general. So in terms of the competition, we're starting to buy stuff starting to come in, but because propulsion, everything takes a while because our what we need, it's a special order. They need to make it for us, so it's gonna take a while before it comes in. Hopefully, it comes in mid March, or end March, early April. When it does come in, I'll try to set up times for us to go in person and either have you guys put stuff in or I can show you guys how I put stuff into the rocket. If you guys do want more hands-on experiences, I would like that you guys get into the rocketry. Here's an example of what we're doing in rocketry. Here's here's my little rocket. It's only half of it. There's the other half. So if you guys want more hands-on experiences, get into rocketry, and we can build rockets and make them go whoosh. There's a video out there of Maciek's amazing rocket, the first one. It was very powerful. We loved it. Um,
Supersonic.
yeah, it did go supersonic. We have data to prove it too. But yeah, so in terms of the propulsion team, that's what's going on. I'm gonna try by the end of semester to get hopefully a level 2 certification so we can test out some student made motors. That might take a while though, because one of us needs to get a level 2 certification. I don't have one. I don't even have a level 1. Maciek probably will get his level 2 sometime soon. But when that does,
Hopefully.
hopefully when that does happen, we can make our own motor and make it go whoosh. All right, Maciek, you can take over now.
All right, guys. So we've prepared for you a series of seminars. The aim of these seminars is to make our own rocket motors, which we're gonna need for our next year's entry in the competition in student-built motor category. So today's seminar is just going to be like a brief introduction to rocket science, just to get you guys general feeling for what it's all about. Here we go. So how rockets work? Well, the basic principle is very simple. It's like action reaction. Okay. So to give you an example, when you're on a skateboard and you throw some heavy object, you'll feel that push back. All right. So in physics, whenever you act with some force, you always have the opposite force acting back on you. Another example is when you shoot with a gun, you'll have that backfire that pushes onto your arm. And actually, balloons are very similar in working principle to rockets. You've got some gas that wants to escape. It escapes to one side, and then the momentum is created in the opposite side that pushes the entire balloon or a rocket. Okay, the most fundamental equation, the rocket equation, invented by this guy, a Russian scientist, Tsiolkovsky. This equation tells you how much speed you can get. Here's a very nice derivation if you're interested in details, although it's a little bit complicated, so I recommend it if you're really into maths. Okay, let's discuss what each term means. Delta V, this is the change of velocity, okay? With this equation, it gives you the maximum theoretical possible change in velocity, assuming that there's no aerodynamic drag or any other like resistive forces. VE, this is effective exhaust velocity. What effective means? Well, it's exhaust velocity with a little bit of addition due to pressure difference. We'll discuss it in the future. ln is natural logarithm. And now m0 and m1, it's very simple to remember. M0 is your starting mass, m1 is your final mass. So the difference between them is the propellant that you burn throughout the mission. Okay, let's give you an example. Let's say that half of your rocket mass is propellant. We assume a typical exhaust velocity of 4 kilometers per second. You plug in the values into the equation, and you end up with 2.77 kilometers per second. So that's really fast. Yeah, so that means if you have like half of your rocket filled with fuel, and you burn that entire fuel, if we ignore, aerodynamics, if you ignore gravity, you will accelerate by exactly this value. Obviously, like the more propellant you have, the greater that number will be. Okay, just to give you a bit more feeling about what delta V is. V, the orbital velocity is 7.7 kilometers per second. What is an orbital velocity? Well, basically, if you want some object, let's say a spacecraft, to travel around Earth and never come back to Earth, you need to fly it, you need to accelerate it at exactly that speed. If it's a bit lower, then at some point it's going to fall back to the Earth. If it's a bit more, it's going to just fly on a bigger orbit, on a greater radius. And if it's much more, if it's like above 11 kilometers per second, then it's going to fly away and never return to Earth. So this is just an approximate, this is like theoretical value, 7.7. But there are also another effects you need to include. There's aerodynamic drag, there's gravity that keeps pulling your rocket back to the Earth. But there's also something that we could use to our benefit. This is rotation of Earth. Keep in mind that Earth like spins around its axis, and that's why rockets are always flown from west to the east to make use of that rotation. And that can actually give you up to 0.4 kilometers per second. It's not much, but it's still worth it. Just keep in mind that in rocket science, every detail is important. So yeah, if you add all that stuff up, you need like 9 kilometers per second. So, compared to our previous, example, we had less than 3 kilometers per second when half of the rocket mass is propellant. In fact, you need like 80%. 80% of rocket mass has to be propellant in order for you to be able to, get to the orbit. And that gives us very little room for payload. It could be, I don't know, 1%, because, you also need a lot of room for structure, right? Structure is heavy too. Okay, so getting back to how rockets work. Do you guys have any questions? Feel free to interrupt at any point. Okay, no questions. Fine. Okay, rockets work based on combustion. For combustion, you need two things. You need fuel and you need oxidizer. Fuel plus oxidizer, this is a propellant, right? Keep that in mind. So we've got these two, we mix them, we ignite them, we've got some energy. Okay, typical fuels. For liquids, liquid propellants, very common is liquid hydrogen. This is the most powerful one, the most energetic, but it's also the most dangerous. It's difficult to handle, and it's not a very common choice, actually. Kerosene used to be very popular. I'm not entirely sure, but I believe that's what was used in Apollo mission to get people to the moon.
Now,
Uh,
also, just a quick side note: if you
uh,
guys ever do research at IIT for any of the professors, and they use any sort of fuel, most of the time what they're going to use is a mix of kerosene. They're going to mix kerosene into some sort of engine fuel, and that's what we use on IIT at IIT in terms of fuel for any of our propulsion systems. Because that's exactly what I use for my propulsion system for the research I'm working on right now. Kerosene is the most readily available. You can get. We have, I think, a 10-gallon bucket. Literally, it's a 10-gallon bucket of kerosene sitting in our research lab. So, kerosene is what you'll usually see in terms of smaller, more sustained rockets. Not rockets, propulsion systems. Sorry, good.
Mhm. Yeah, it's also the most popular aviation fuel, but the kerosene that is used for rocketry is slightly different. The one that is used for rocketry is denoted with symbol RP1. And then probably the most popular liquid fuel nowadays is liquid methane. I know that SpaceX utilizes it, and I'm pretty sure a couple of other companies too. It's not as energetic as liquid hydrogen, but it's much nicer to work with. Okay, in terms of solid fuels, charcoal, sugar, anything that has carbon in it can burn, so it can be a fuel, but there are also metal-based fuels. I certainly heard about sugar rockets. They're popular, there are a bunch of YouTube videos how to make sugar rockets. This is essentially mixed sugar with potassium nitrate and a little bit of sulfur. Instead of sugar, I recommend charcoal for safety reasons. We'll discuss it another time. But yeah, came back to metal fuels. Could use aluminum, magnesium. These are typically additives to your fuel. So sometimes you may have, mixtures of various fuels. Now, in terms of liquid oxidizers, almost exclusively in big launches, you have liquid oxygen. But for small research, nitrous oxide is very nice to work with. And finally, solid oxidizers. There are only three really worth mentioning. There's ammonium perchlorate, ammonium nitrate, and potassium nitrate. The first one is the strongest, the most powerful. The last one is the least powerful and the safest. So we're gonna start off with that one. Okay, so let's get back to the idea of balloon. We've got combustion, we've got some energy, we've got some gas with very high pressure and temperature. So in other words, it's potential energy, and we want to convert it to kinetic energy. Okay, we want to convert that energy into velocity, and it's important that it goes in some specified direction. That's why we have nozzles. So yeah, looking at the equation, we want to maximize VE, the exhaust velocity, and that's the main goal for the nozzle. So what should be the geometry of the nozzle? You probably heard about the trick with garden hose. If you cover it partially with your thumb, the water flow, increases in speed. Why it works that way? Well, basically, if you have smaller cross-sectional area, you need increase in speed so that you maintain your flow rate. This is called conservation of mass. But this works only up to speed of sound. So looking here at a typical nozzle diagram, up to speed of sound, initially you have convergent section. So just as I described, as your area decreases, the gas increases in velocity, it accelerates until it hits sonic speed in the throat. And then beyond that point, physics kind of work, in a reversed way. From now onwards, once you have that sonic speed, when you increase the area, the velocity continues to increase. And there is a really nice explanation in that YouTube video. So I came back to how it looks on the real rockets. This is the F1 engine from Saturn V, which brought humans to the moon, you can see that majority of what you can see is the rocket nozzle. Let me see, where's my cursor? Oh, there it is. Okay, you see, so this part, this entire thing is rocket nozzle. The rest of the engine is here. Here you've got combustion chamber, you've got that convergent section, and then you've got that divergent section. Okay, I'm gonna let Mo take over now.
Alrighty, give me 1 second, guys. Bada bing, bada boom. There we go. Alrighty. So far, what you guys have looked at is how rockets work. Now, in terms of model rockets, how are they classified? How do you? So for our competition, we're getting off the shelf rocket. Well, how are these off the shelf rockets classified? How do you know which one to get? So this chart here gives us a basic idea of how model rockets are classified. Um, there's something called total impulse, which I'll go over in a second. And with that total impulse, there's a range, and within each range, there's a classification letter. So you would get an E rocket, a F rocket, or a G rocket, and each one of those rockets have their own size, what size nozzle they need, or what size fitting they need to go into. So what is this total impulse? Total impulse basically is the amount of force this rocket produces over a specific time. So let's say at this point right here is where I light up the fuse for the rocket. That means it goes on for a while. It gives off a constant amount of force, and then it stops burning. So the total impulse is we're going to add up all of these forces for that given amount of time. We're going to multiply them together, and that's going to be your total impulse. Now, why is total impulse? Why are they classified with total impulses? Well, total impulse, when you do the calculation, which you guys are gonna, if you guys are in propulsions right now, later on the semester, you're gonna hit a chapter where you're gonna take total impulse, and there's a conversion that takes you from mass straight to altitude. So if I know what my mass is from that delta v function that Maciek showed you guys, that's where the total impulse comes in, because that the velocity exit goes away, and the total impulse equation comes in with a g0. So you can take this mass, and you're gonna put it in that equation, and it's gonna tell you what's gonna be your maximum altitude. And later on, when we're gonna show you simulations that we do of these rockets, you put in what your mass is, and it tells you for a specific rocket with your total mass, this is how far up your rocket is going to go. When Maciek launched his rocket, what was the name of the software, Maciek? Do you remember?
Software, Open Rocket.
Open Rocket, yeah. So in Open Rocket, you put in your total mass, you put in a rough design of what your rocket looks like, and it tells you, hey, for this mass and this motor, this is how far up you're gonna go roughly, and it's pretty close. Yeah. So in terms of model rockets, there's only three different kinds of model rockets you can buy. One is black powder. The name says it. It's just black powder. You light it, it goes. It's a one-time use. You put it in. It's just you light it up and it goes off. Another type is a single or a reusable composite motor. This is what Maciek showed you guys earlier with a fluid, a fuel, and an oxidizer. That's what this is. Basically, you have your black powder and you mix it with some kind of oxidizer, and you burn the oxidizer, you burn the black powder, creates more of a force at the exit, or more velocity at the exit, which gives us more power. These are called composite motors. And the last is hybrid motors. We're probably not going to be doing much with hybrid motors, but these are what we would use as liquid oxygen or some sort of liquid fuel to basically get the force we need. These are a little more dangerous. You need for any of these, if you're gonna make them by hand, you need a level 2 certification. And most of the time, they suggest you don't work with hybrid motors. They're a little tricky to work with, so we're probably not going to be working with hybrid motors. So in terms of propulsions, it's not just the motor that we care about, but everything else that goes with the motor. So I'll show you my rocket as an example. So this little hole right here, that's where the that's where the rocket motor goes. And for example, let's say it's going to produce 20-pound force of thrust for 5 seconds. That means constantly for the next 5 seconds, it's going to be pushing back this way 20 pounds. That's a lot. So if the motor is in here just by itself right now, you let go of it, what's going to happen? What's the rocket's going to go to the side and the motor is going to fall off, right? Because there's nothing covering it. So you need these rocket motor covers right there. These rocket motor covers. That's what you need to hold the motor in place so that it doesn't fall off or it doesn't go back the other side. These right here, these are what holds these together and holds the motor in place. So let's say if you turn the motor on, it's pushing this way, right? This ensures that the motor doesn't go the other way into your rocket and comes out this way. And these right here is this stuff. These O-rings, it's what you align with your motor to ensure that when the motor is in here, it stays at a 90 degree. So let's say if it's not a 90, let's say it's like an 89. As soon as you let go of the motor, right? You light the fuse, the motor starts. What's going to happen is it's going to go up, but the motor is at an angle. So there's a force pointing this way. Your rocket's going to do one of these, and it's going to turn back around on itself. This right here is the motor cover. We're not going to be using plastic too much because these motors get really, really hot. I mean, we're talking like pretty hot. So this right here is sort of cardboard plywood kind of thing. This for level 1 and 2 purposes is pretty good. When it gets to level 3, we're probably not going to be using these. We're going to be using some sort of metal. Those plastic ones are good for low level impulses, but since we're going to be working at almost level 1 impulse motors, we're going to be using something like a plywood, cardboard mixture, or metallic mixture. In terms of our competition, we've got something different. It's metallic. We're using a reusable motor. That means the outer casing is metallic. It goes and the propellant goes inside this metallic casing, and the metallic casing then has all of these combined at the end of the motor at the end of the rocket to ensure that when you light the fuse, the motor doesn't go into the rocket, come out of the other side, or go at an angle and mess up the entire launch. If you guys haven't already seen on the Slack page for propulsion, there's a video of Machek's level 2 certification. These things are powerful. They're pretty powerful. If you hear it with the audio, you can hear how loud these motors are. And I suggest if you guys have the time, this is an hour-long lecture. I don't expect you guys to watch this. It's a pretty long lecture. But if you do watch this, it gives you an idea of... So far we've been talking about off-the-shelf motors. This video right here shows you how you make your own motor, which is what we're going to be doing for the next competition, which is going to be next semester. So in that case, if you guys have the time, it's about an hour long. The dude's funny and amazing. You should definitely watch that video. But at this point, do any of you guys have any questions for us? Or for me, or for Maciek, or in general? Do you guys, if you guys want to build a rocket like this isn't mine. I didn't build this. This was provided to me by SEDS IIT. I'm in the rocketry club with them, so I get to build crazy stuff like this. This is actually the half of it. There's the other half that goes here. It's gonna be added later on. So this is a huge one. I didn't realize this. But if you guys are looking for sort of hands-on, fun things to do, and you don't worry about being a nerd, then this is fun stuff. You can try this. But other than that, do you guys have any questions?
Building your own motor seems kind of dangerous.
It is very dangerous. That's why they want you to have a level 2 certification before you can even test these out.
Okay.
Yeah, and we're probably going to be using so we can't test these at inside IIT. There is a
Hmm.
specific location where you can test these. If you guys have ever been to the RE building, the back end of the RE building that connects to, I don't know which building that is, but there's back end of IIT. There's a big old turbine out there, and right next to the turbine there's a pole there. That location is the only location where you can test these out. You need to have a specific stand, a stand that basically tells you how much thrust you're producing. Um,
Mhm.
and you're gonna have to talk to AIAA because they're the ones who have that um, thrust plates, the thrust collecting. I don't remember the name of the thing. It's something that reads out the
We
thrust.
could we could always build our one load cell.
Can we?
Yeah, this is pretty important thing, but I think even more important is pressure transducer that's going to tell us, what pressure, how pressure varies throughout the combustion. It's even more important than the actual measurement of thrust because you can calculate thrust from it. And
We need to.
pressure gives you like way more information because you can also like calculate the temperature.
Mhm,
And in case if you get problems with temperature, in case your case burns through,
mhm.
you will see it just from your measurements.
Macho, do you have an idea what the temperature is off of at the end of these? Any idea? I
At
don't know.
the end, like
Yeah.
it depends like which part are you talking about because the combustion is like thousands of degrees Celsius, right?
Yeah.
But outside of the motor, right next to it, something on the order of hundreds.
Okay.
I'm talking like even maybe 800,000 degrees Celsius.
Okay.
So
Yeah.
no, 800, no, that's a bit of an exaggeration, but sorry, but more like three, 400. Yeah,
Um.
I'm not gonna give you exact value because obviously it varies.
Right.
But I just realized that for the rockets that we are building at SEDS, we
Mhm.
need epoxy rated for higher temperatures.
Yeah. Especially for this end, right? Especially
Yeah,
because I don't know if you
there's
guys
a
have
risk.
seen there's a weird orangish weird stuff that's the epoxy. That's
Yeah,
what's holding this stuff together. This is epoxied up. Uh, but I now have to make sure that it's actually rated for the right temperature, which we're gonna do
yeah.
probably.
So
Yeah.
Mo used 5 minute epoxy, which is great because it settles down in 5 minutes. But we are not sure if that's not going to melt during lunch.
Right.
We'll see how it goes.
We'll see. Yeah, I'll be hopefully launching March 20th in
Mhm.
Wisconsin. So if any of you guys want to go out there and watch this launch, let me know. Uh, we can either figure out one of the IIT cars. That can probably talk to IIT to get us a car. If not, we can drive there. I got my own car. I can take up to 3, 4 people. But yeah, are there any other questions?
Yeah, I just want to continue about like what Peter said. Yes, making our own motors is dangerous, and number one thing is safety. I've
Right.
got some experience. I'll tell you guys how to do it, but the most important thing is that we start small. We're gonna build motors of the size of a finger. Okay, probably we're gonna start with black powder motors, and I'll show you exactly what to do to make it safe. But probably the greatest challenge will be to convince IIT to allow us to do this. We'll need to get some insurance and so on. But I'm pretty sure it's a matter of time, but I'm pretty sure we'll eventually get it.
Hopefully.
And
All
then, what size motors can we actually launch at IIT? I imagine we can't do something too powerful.
So,
We can't launch anything at IIT, I
Oh,
believe. Yeah, these all these motors are going to be launched at the launch sites.
okay.
yeah,
We can test them, as in we're going to put them on a test bench, and it's going to go off, and we're going to read data off of it. But in terms of going at
Uh,
an altitude, they're not going anywhere. Yeah,
okay. Yeah,
yeah,
that's what I figured.
yeah,
Okay.
yeah.
yeah, but still, even for those tests on site, we're gonna have some limit. I'm not sure what the limit is,
Okay.
but
I mean,
Yeah, I doubt they would allow us to use high power rocket motors. So anyway, we need to start with small motors of the size of my finger, just
Mhm.
made from some, PVC tubes. Yeah, I've got some experience with these. And if we could get some data on it, any data, that would be great. If
mhm.
we could get, pressure inside, that would be ideal. That would be perfect.
The pressure transducer we're using for our research, it was a 25 buck pressure sensor. Reads up to, so the at the nozzle exit, not the nozzle exit. We're getting data straight off of a compressor. That pressure transducer, it's rated for up to 500 degrees Celsius, and the temperature rating for our purposes, it's 450. So that's why we're using this one. If we can first we're gonna have to get IIT's permission to do anything. But if we do
Hmm.
get to that point, we can get a pressure transducer and a temperature. There might be something out there. We can have Craig build us a little nozzle that's gonna go after the motor, and we can just have two of these in there to measure out everything that's coming off of it.
Hmm.
Yeah.
Yeah, Mo, I think during next meeting, our leadership meeting, we
Hmm.
should discuss it, with the entire leadership, that we
Right.
want to start the process, of like getting permission from IIT to do that stuff.
Right. Alrighty. Any other questions, guys? All right. This video is going to be up on Slack in a bit. If you guys missed anything, if you have any of the questions, feel free to contact me anytime. I'll probably get back to you within a couple of minutes. If it's something that's like I don't know about, I'm probably gonna just reach out to Maciek and ask the question. So, but yeah, feel free to contact me about anything related to propulsions. Um, if if you guys are taking propulsions class, you're gonna see those equations that we just talked about come up sometime soon. Um, Fun fact: that equation that you saw, the delta V equation, that equation is the entire reason why we don't do one single rocket. We do multiple stage rockets. That is the entire reason why. But yeah, other than that, if there aren't any questions, I'll end it here. I'm gonna stop recording first. That one first.